Hello everyone, welcome to the last meeting of Conversational AI Reading Group of 2024. Today we have the pleasure of having Mirco Ravanelli presenting his work on discrete audio tokens for multimodal LLMs. Mirco Ravanelli receives his PhD from the University of Toronto. He is currently an assistant professor with Concordia University and an adjunct professor with the Université de Montréal and a Mila associate member. He is the founder and leader of the SpeechBrain project, which aimed to build an open source toolkit for conversational AI and speech processing. He is the author and co-author of more than 80 papers on his research interests, which include deep learning and conversational AI. He is an active member of the speech and machine learning communities. Please welcome Mirco Ravanelli to the stage.
All right. In particular, I would like to discuss how we can integrate the audio modality within multimodal LLMs. So this presentation is mainly designed and conceived for people that are kind of already reasonably expert on deep learning, but they want to learn something more about the way we can add audio modalities. So let me start from the beginning, right? So from language models. So even though some people might have might perceive a language model as something new, the reality is that language models have a long history, really a long history, and they actually were designed back in time to assign probabilities to every sequence of words. Like you wanted to see to check if some kind of sequence of words were more likely than others. Right, and if you would like to compute this probability, you can factorize this probability, the joint probability of observing word 1, word 2, word n, as the probability of having word 1 times the probability of having word 2 given word 1 plus, times the probability of observing word 3 given word 1 and 2, etc. So it turned out that you can compute this probability just by solving this task, which is about predicting the next word giving the previous ones. And this is actually what language models are trying to do these days as well, right? So they are just trying to predict the next word. And it turned out that this task, despite being relatively simple in the way it is defined, it turned out that it is actually the task that trigger the level of intelligence that we are observing in large language models these days. So everything started with n-grams. In n-grams, you have like truncated history here. So you cannot go through a long history, but just you truncate to 2, 3, 4 previous words, right? Then you apply some kind of like counting strategies and smoothing strategy to have better statistics. But that's pretty much what we do with n-grams, which were dominant, I will say, until 2010 approximately. At some point, people realized that just like counting-based approaches were very limited, and people realized instead that it was better to use neural networks for this task, because with neural networks, you might have like kind of a continuous representation that can generalize much better. There is a famous paper by Joshua Bengio, right, in 2002, actually arguing the potential benefits of language models trained with neural networks. Then, after 2010 to 2018, people started to, integrate longer and longer context through RNNs, and after 2018 to now, the dominant approach is transformers, which are particularly suitable for this task because we can scale transformers a lot and have the performance that we are observing these days. So I think overall, large language models are pretty conceptually, at least, pretty simple models in the sense that they are just like they're different architectures, of course, but most of them are autoregressive decoding transformers, which are trained to predict the next word, which means that, for instance, you may have like um, uh, some word in input, and your goal is to predict the next one, right, with transformers in an autoregressive way. And the most surprising things behind this architecture is that it turned out that if you massively scale up this model with tons of data and tons of parameters, the performance becomes crazy impressive, right? So you reach the performance that you can have with models like ChatGPT, etc. And that's, if you want, is the most surprising thing to me, right? So only few people, I think, in the community believe that the only way to go, let's say, was just like blindly scaling the technology we already have. Like one of them is for sure Ilya Sutskever, who was like at NeurIPS last week, who firmly believe in that. But many others, including, I guess, myself, thought that we had to go to do something something more convoluted or complicated to achieve the performance that we are observing these days. Instead, no. Instead, scaling up everything was just like the key. However, these days, large language models, are evolving very fast. And you have seen that the first large language models were only based on text, but these days you can use multiple modalities. For instance, you can have audio modalities, video modalities, images, and of course text, and all these modalities are mixed together. Of course, multimodality offers several advantages. First of all, it offers a deeper understanding. If you cross-check multiple modalities, you can understand much, much better the world around you, right? Better generalization, right? So also in this case, observing multiple modalities can definitely help generalizing well, right? One modality can be more informative than another in one context and vice versa. So overall, I think you can generalize better with that in principle. You can hopefully have fewer hallucinations, right? Because, the reply of the system should be consistent with the modalities. And hopefully also this makes the technology more accessible, because you can really select your preferred modality to interact with the machine. So of course, everybody is going in this direction. And there are different architectures to evolve this LLM, this traditional text-based LLM into something multimodal. And one architecture which is particularly convenient and particularly popular these days is about injecting all the other modalities by tokenizing them. It's like we are not only tokenizing the text, which is something relatively easy to do, but we also tokenize the other modalities, including the audio and images, if any, etc. And yeah, there are different ways to inject this information. One way, which is particularly convenient, could be to have all the modalities in parallel. Like, for instance, if you want to have like the audio modalities, you can inject the audio tokens in parallel. You may have seen that normally you have more than one code book for audio tokens, because audio is a little bit more informative than just plain text, so we need more information in input. But apart from that, the concept is the same. You just like text, you tokenize audio, and you feed that into this architecture. This architecture specifically is particularly convenient because you can have it allows like a kind of real-time conversation with the machine, because you can have like you can speak to the machine, right, and collect these audio tokens, and then the machine can reply to you in either in text mode or in the audio mode. And there might be also some kind of overlap between what you ask the machine and the reply of the machine, making everything more natural, etc. So this is actually an architecture that many people are using, and including Qt, which has recently, maybe you have already have seen, recently released a kind of open source model for that task. So.
We could not hear the voice, Mirco.
Can you hear?
No, we could not hear the voice.
Okay, but it was just like a demo, right, showing that you can use this architecture in a real time to converse with a machine in a pretty natural way. Okay, yeah, let me move on. But what's the problem with that? Um, tokenizing text, I said, is relatively simple because text is discrete in nature. But audio and speech signals are continuous in nature, right? So discretizing them is not as natural as like creating text tokens. So for instance, if you think about the original waveform that we use, typically, the original waveform, you may argue that the original waveform is not really formally continuous because there is like a digitalization of the waveform that goes through a sampling, which is a discretization in time, and quantization, which is a discretization in the waveform amplitude. But the reality is that the number of samples and the number of amplitude levels is so high that you can definitely approximate the waveform as a kind of continuous signal. Also, when we use something on top of that, right, like we typically use time frequency representations like the spectrogram. Also, in this case, every time frequency bean is actually a continuous number, a real number. Even when we kind of try to make the representation more compact, for instance, computing filter banks, where we actually try to compress the frequency scale with MEL filters. Also, in this case, every time frequency bean is definitely a real number. These days, we work a lot with self-supervised model, Way2Vec, Uber, WebLM, just to name a few, the most popular one, and also the representation that these models they compute are actually continuous. So the problem here is the following. Sorry, how can we discretize audio and speech without losing information? That's really crucial, right? So how can we do that? That's an open research question if you want, even though in the last few months, the community has done a lot of progress on that topic. So broadly speaking, I'm gonna be very general here because there's no time to discuss all the works that are coming out these days because there are just too many, and every week a new work come out. But generally speaking, we can the current audio tokens can be categorized in two ways. Like one category is compression tokens, also called audio tokens. This kind of audio tokens, compression tokens, were not really designed for multimodal LLMs, but were mainly designed for data storage, transmissions, and these kind of things. However, they can be used for multimodal LLMs as well. And the way it works, a very high level, is the following. So you start from a waveform here. You apply an encoder, which is just a neural network, can be a convolutional or any kind of neural network that try to compress the information in the waveform in some kind of latent representations. In the bottleneck, you apply quantizer, like vector quantization, typically residual vector quantization with multiple blocks, and you learn a codebook which tries to describe as precisely as possible your input signals. Then on top of the quantized features, you apply a decoder which tries to reconstruct the original waveform. And if you train this model in terms of data, etc., you can learn kind of good representations which are discrete in nature. There are many papers working on this approach. It's definitely very promising, and examples are just a couple of examples are Soundstream and Encodec. They are a little bit more complicated than that, but that's the main idea. In another line of research is to use the so-called semantic tokens. I don't really like too much the term semantic tokens, but essentially what we want to do here is to take one of the pre-trained models, pre-trained SSL model I mentioned before, for instance, Way2Vec, WaveLM, Hubert, and somehow quantize their internal representations. So just to be concrete, these models are going to provide continuous representation at every layer. So at every layer, you can apply some kind of clustering algorithms, for instance, based on k-means, which are going to discretize your representation, and these are the representation that you use for your downstream task, essentially. So instead of using the continuous representation, you use the corresponding discrete version of this representation after applying clustering. So, as you may imagine, this operation is very critical, and if you don't do it in the right way, you lose a lot of information, and your audio tokens in the end will be really poor on many tasks. So with Pune, right, at Interspeech, we presented this paper, which provides some insights about how we can learn good discrete audio tokens from these self-supervised representations. So let me go quickly through it. So there are many actually design questions that you need to be aware when you design the audio tokens in this kind of way. One basic question should be which layers we should cluster. We should cluster layer 1, layer 2, layer 7, which one? Then there are other questions like how many clusters do we want to actually highlight from our data? And which data set do you use for clustering, right? So at some point we need to decide on which data set we identify our discrete units, and also how can we train a vocoder that reconstructs the original waveform starting from the discrete tokens that you have identified in through clustering, and also how do we initialize the embeddings effectively. So that's also something I will go through that later. And can we extract in this way? That's a very fundamental question. Can we extract tokens which are universal and in the sense that they work for both discriminative and generative tasks? That's actually what we try to address in this paper with Pune. And our approach was the following. So we apply a pretty standard pipeline for clustering, like we clustered all the layers, all the L layers, right? For instance, we identify the L layers to cluster essentially. Then on top of the embeddings, right, of each layers of the embeddings corresponding to the tokens we applied an attention mechanism, right, and we kind of summarize everything into a single stream. Then when we have to do discriminative models, right, we just feed these tokens into a discriminative models, for instance, an ESR model, speaker verification, etc. And this model is try to do some prediction. When we want to use these audio tokens into a generative models, instead, what we have to do, typically the generative model these tokens will be produced at the output, and we need to convert these output tokens into the waveform back with a vocoder And in that paper, we proposed something called scalable vocoder, which turned out to work pretty well, and it is able to operate different bit rates with different layers combinations. So you don't need to have like a specific layers, right? Because we train with layer dropout, you can feed it a variable number of layers, and it works pretty well. So we run experiments with this setup. Actually, we consider at the beginning 6 tasks. Like one is categorized in discriminative task and generative task. For discriminative task, we consider automatic speech recognition, emotion recognition, and speaker identification. For generative task, we address speech enhancement, text-to-speech, and scalable vocoder. Of course, you can find all the details about the dataset in the paper. But the one interesting observation, which is actually in line with what people already observed in continuous representation for of SSL model, we notice that it's very important to distill information from all the layers, because for some kind of task like TTS and speaker verification, the downstream tasks seems to prefer information from the lower layers. That's actually kind of expected. For other tasks like speech recognition, instead, you prefer to have like high-level information. And for other tasks like speech enhancement, for instance, all the layers provide useful information. So this is a kind of important things, maybe not that very surprising, but it's very important to remark that our audio tokens, our ideal audio tokens, should have information with different level of granularity, with different level of abstractions. So we definitely need to keep that in mind to develop very effective audio tokens. Let me show you some numbers. Sorry if there's a kind of big table, but I can go through it and just like share with you the main observations. So in this table, actually, we compared the performance on the discriminatory task and also on the generative task with different kind of settings. So here we try different number of clusters and different ways to initialize the embeddings. So what turned out is that approximately we found that 2,000 clusters provides good performance, right? In some cases, it doesn't make too much sense, at least for the application we are targeting, to have too many clusters. That's good, actually. We also studied how we should initialize the embedding of in the downstream task. Like, so essentially in the downstream task, for every token, right? For every token you have, you need to assign an embedding vector. The simplest approach consists to do that randomly, but you can do also something which we thought was clever, like instead of having the random initialization, you just initialize the embedding with the vector corresponding to the k-mean centroid. But it turned out that this is not really effective. So it is fine having, once you identify your audio tokens, the embeddings of this audio token can be initialized randomly without losing performance. The other big question I also mentioned before is how can we, on which data set we should extract these tokens. Here we did a couple of experiments. In domain means that we use the tokens from the same data set, right? We use here, so it's a kind of experiment that actually provides some kind of upper bound of the performance, while out of domain, like the data set that we use for the downstream task is different from the data set we use for identifying the tokens. And it turned out that, of course, the in-domain scenario works better, but the encouraging part is that also the out of distribution, out of domain experiment show competitive results, so the performance is not always hugely degraded, making us confident that we can learn general tokens, which actually works well for different tasks. Then we did this initial study that we actually presented in the speech, but we weren't very happy, so we wanted to go even further, and we asked ourselves, are compression tokens better than semantic tokens? Remember, I introduced the two tokens before. Compression tokens are just like typically autoencoders with some kind of discrete bottleneck in the middle. Semantic tokens, instead, we use SSL models and we try to cluster them, their representations. We didn't actually, at that time, we didn't find a clear answer in the literature. So we created our benchmark ourselves, which is called DASB, Discrete Audio and Speech Benchmarks. And these days there are other benchmarks such as like in the SPNet, they have their own benchmark, and also there is super code. But we are also contributing with our benchmark, which is a little bit different. And we called this benchmark Discrete Audio and Speech Benchmark. So what we found in this work is that, first of all, we actually tried to benchmark different type of tokenizers. These days, we are expanding the benchmark to address even more, but at that time when we started the paper, these were actually the dominant one. So we had like some kind of semantic tokens, like discrete version of Uber, discrete version of WaveLM, discrete wave2vec, and some compression-based tokens like encodec and DAC, and speech tokenizer, which is actually a combination of the two. We address multiple tasks like, again, discriminative and generative, speech recognition, speaker identification and verification, emotion recognition, intent classification, keyword spotting, speech enhancement, separation, and TTS. And we try to see in a kind of control way and control scenario which one, if like these discrete tokens, these semantic tokens are better or not than compression tokens. So here we did tons of experiments, and also we have like a big table here showing, in this case, the results of the discriminative task and for different bit rates, and also comparing the results with the continuous baseline. So out of this big table, what are the highlights? I think, first of all, we have to say that for this discriminative task, ASR, etc., semantic tokens performs better than compression tokens. That's a little bit expected, but we definitely confirm in our results. We only noticed that semantic tokens, they all suffer a lot from speaker to kind of encode properly the speaker information. Actually, I just came back from NeurIPS and I saw a paper which aims to fill this gap. But naturally, this this kind of semantic tokens lacks. They suffer from this problem, and it's important to inject this information somehow to have better tokens. But the other big thing that we noticed is that if we compare the results with discrete representations, even the best results of the discrete representation with the standard SSL model, like for instance, based on WaveLM, you can see that there is a big gap compared to the between the discrete baselines and the continuous. That's actually should trigger some kind of reflection because the gap is still pretty big. So we should ask ourselves if really these discrete tokens are the way to go, or there are other ways to inject audio information into a multimodal LLMs. We also did the same thing for generative task, and what it came out is that also in this case, and this is a little bit more surprising, the semantic tokens are on average performing better than the compression-based tokens. And I think the trick here is to learn a very good vocoder, right? And as long as you have a very good vocoder, like the scalable vocoder we mentioned before, these kind of semantic tokens become, at least for what we see now, better than compression tokens, at least for now. But still, the other big remark is that also for this task, we observe a big gap with continuous baselines. So this also make more evident the need, the potential need to have better, either have better discrete audio tokens or rethink the way we inject audio information into the LLMs. So we wrote a paper, we actually came out with a rank, and turned out that among all the audio tokens that we use, the best one is like a discrete WaveLM. Like a discrete version of WaveLM give us, on average, the best performance, right, on a generative and discriminative task. And you can see the compression-based tokens are not as competitive, at least to the task we have considered now. So the main outcome of DASP is that whatever we do, actually, we are still far from an ideal solution. We have seen that semantic tokens, at least for now, I'm not sure what is going to happen in the future, but for now, to us, they give the best performance, but they are very expensive, computationally expensive compared to compression tokens. You may argue that in a multimodal LLMs, the main network, like the main transformer, is so big that computing the audio tokens like only takes a marginal amount of time, but still will be great to have something more compact and less computationally expensive. We have seen they do not preserve identities as well, and we also have seen that there is a very significant drop in the performance compared to continuous representations. So actually, we have implemented the DASB in SpeechBrain, right? In SpeechBrain, there is a new repository for benchmarks, and you can find DASB there. Let me just say that many more tokens. We are expanding it towards audio and music as well, and a follow-up pretty soon. But everything will be merged in SpeechBrain. So this is what we have seen so far. So what about the future? So I think by universal audio tokens, I just mean tokens which are really suitable for multiple tasks at the same time. So when people use multimodal LLMs, it's very likely that they will use for tons of different tasks, right? So we need some kind of general and universal audio tokens that can be good for emotion recognition, speech, audio editing, and all this. And this actually, I don't think we are all there, at least according to what we have seen. And here are some ideas that I think can potentially work. For sure, I think we need to go towards massive multitask learning. You may have seen that the compression-based tokens these days are mainly based on a single task, in some cases a couple of tasks, because they use also contrastive learning, but it's not really definitely massive multitask. My team actually during my postdoc, I actually explore this massive multitask learning in the context of like standard self-supervised learning with a neural network called PACE. And I think there should be something similar to do here. Like we can, my feeling is that we can create audio tokens which are really universal only if we really go towards like we train them on massive multitask learning, where the task can be self-supervised or even supervised or weakly supervised. So I think we can do better if we extend audio tokens. They will improve the way we learn audio tokens through this massive multitask learning. Then I think we need to have like more hierarchical code books, right? The speech, right, has like this hierarchical informations in multiple levels, right? Phonemes, words, emotions, etc. And I think we have to learn this code book to encourage this kind of structure which is present in speech. I think we need also to put more care about the perceptual loss optimizations. Like I envision that one of these tasks could be something similar to what we have done with the metric gun, where you may have like a specific task which is about perceptual loss optimization. And also, like connected to what I said about hierarchical codebook, we really need to better address the fact that speech is multi-scale and is providing information at different level of abstractions. So another direction that I think is very important is about interpretability. So our team is working a lot of interpretability, and I think we really need some kind of interpretable audio tokens. What I mean with that, like let me compare the text tokens and the audio tokens. In the text token, it's pretty clear what is happening, right? The text tokens are just grouping characters together, right? So for every token you emit, you have a clear connection with the characters, right? So you can easily interpret the meaning of each token if you want. But for audio, it's very different. For audio, let's assume you have your audio and you extract your audio tokens. What you see is just a bunch of numbers like that, and you will have like a very hard time mapping these audio tokens to some kind of specific features in the waveform or in the spectrogram. So that's bad, and I think there is room here for improving. The way I see that is to add some kind of constraints in the codebook we learn to make sure that the codebook, every element in the codebook, is connected to some kind of local properties in your input signal. For instance, you may want to have some codebook like kind of modeling some kind of line in the spectrum. You may want to have codebook modeling some kind of higher spectral components, etc., etc., etc. And if you do that, you not only increase the transparency and interpretability of the system and make error analysis easier, but I feel that this kind of inductive bias, right, about connecting these tokens with local properties of the spectrogram can provide a very powerful regularization that can not only help performance, but also generalization. That's some kind of interesting direction, and hopefully in my group we will dive into that in the future. The other big question I would like to share with you, I'm definitely not sure that audio tokenization is the best way to go, right? So I think I invite everybody to reflect on that. According to the experience we have in our group, it looks like the tokenization, you inevitably lose a lot of information, right? So there are two ways here to go. One way is to like do more research and having better audio tokenizers, which is something we will likely do, but another totally different way to approach this problem is to, is to just totally revise the way we inject audio into an LLM, right? So it's say, okay, so if audio tokenization is not the best way to go, what are the alternatives? And I think here there might be a lot of room for research, right? Also in Europe, I saw people trying to have models which are in part autoregressive, in part diffusion-based, and these kind of things. And in that case, maybe audio can fit better into the model. Yeah, that's pretty much all. Let me just say that we are working with a very large team, right? Trying to put on a survey paper and an experimental paper where we try to put together different benchmark, DASP, Codex Superb, ESPNet, and others, and kind of have some insights altogether about what are the open challenges and the best way to go for the future. And also, as I mentioned before, we are significantly expanding DASP, and also this will be object of a future publication, hopefully soon. Okay, so let me just say that this work was actually done by my collaborators like Pune, Artem, Luca, Jarod, Salah, and Sam who did really an amazing work on that. And hopefully, if you would like to stay tuned, you can follow. You can stay tuned, right, and see our upcoming publication in this topic. That's pretty much all. So I'm happy to stop here, and I have plenty of time if you want to reply your questions. Thank you very much.
Thank you for the presentation. Okay, so if people have any questions, you can drop them in the chat, or you can just raise your hand and we'll give you access to ask a question.
No problem if you open your mic, and yeah.
Yeah. So yeah, there is a question already in the chat. I don't know if you can see the questions.
Yeah.
Okay.
But I heard some kind of microphone switching on. Is there somebody?
Yeah, it was me, Mirco.
Right. Okay. Good.
Yeah, just a simple question, maybe. So how do you differentiate this like multimodal audio text with multimodal image and text? So why in like image multimodal approach we have a better like tokenization scenario like compared to the audio?
I think it is equally critical, right? So also people working from the computer vision, they complain about similar issues, right? I think most of the models, right, they outsource the image part and they do like diffusion models right on top of that. Yeah, I think the problem is pretty the same. I saw the best paper award and URIPS proposing another way actually to do tokenization. So instead of having tokens which corresponds to different patches of the image, you have tokens which corresponds to different resolutions. So yeah, I think they have pretty much the same problem. I think the multimodal aspect is already pretty good if you want, but there is a lot of room for improvement. That's my impression.
Okay. So basically, I mean, it's possible to use the techniques in the multimodal image text for audio text, but might not work as well, right?
Yeah, I mean, it's pretty much the same problem, right? So you take a signal, whether it is audio or image, and you kind of discretize it, right? That's it.
Yeah,
so definitely.
Right.
Definitely the same problem and similar solutions. Yeah.
Okay. Thank you.
You're welcome.
Is there anybody else who wants to ask a question directly?
Yes. Hi, Mirco.
Hey.
Hi, great talk. I have a question. I saw the interesting results basically from the slide 12 that you dive into some details about the comparison between semantic tokens and compression tokens.
Yeah, let me go back maybe. You said slide 12, right? Okay.
Yes, I think it's
This
yes,
one,
yeah. It's I'm actually quite surprised to see, oh, maybe not 12, it's maybe the later slides where you show that the semantic tokens are not performing very well. Oh, yes, maybe that one. On like for example, the SI, I suppose that's speaker identification,
yeah.
right?
Speaker
Yes,
identification, SI, and SV speaker verification.
Verification, yes. So specifically for these speaker tasks, the semantic tokens are performing much worse than the compression tokens.
Yeah.
Do you think this is owing to how, like the difference in their training objectives, or is it more due to, for example, the use of residual vector quantization?
In general, my interpretation of that is that compression-based tokens, they tend to provide low-level information, right? So low-level information which might contain this kind of speaker information. Like semantic tokens, even though we actually have different layers, on average, they tend to provide higher level information, which make it more suitable for ASR and another task. For somehow the speaker information is not really captured well. But as I said, I think there is already a solution. I saw a paper in Eurips actually trying to fix this problem. So it's not only us that we observe this, it's actually kind of common problem. And yeah, I think the solution is like to adapt the model and making sure that it also captures speaker information. Yeah.
Got it. Yes, you were mentioning that the compression tokens are focusing more on the low level part.
Yeah, because they are trained like that, right? They are trained to reconstruct the signal. Yeah.
Yeah, like I'm looking at the high bitrate part where both the codec and DAC have. Oh, okay, I see. Yeah, so the word error rate, yes, basically. Okay, yeah, that makes sense. Okay.
Yeah, so yeah, there are also like hybrid tokenizer that try to combine the two, but I think we need to improve that, right? So my feeling, as I said in the presentation, is that we need to revise these compression-based tokens, which in my opinion in the future will be the best way to go, but totally revise the training pipeline and using massive multitask training.
Okay, got it.
Because only with massive multitask training you can potentially capture all the information, right? And not just like part of it.
Okay, yeah, that makes sense.
Thank you.
So there's a question in the chat that says, what do you think about the simple alternative of feeding the continuous embeddings directly into the transformer instead of feeding the index of tokens and learning new embedding tables?
Yeah. So, well, when we feed when in a multimodal LLM we feed the audio tokens, right? We feed the ID of the tokens, and we can feed also we can associate to the ID a continuous representation that we can learn. Typically, this is what we do. An alternative is not using audio tokens at all, but just like inject continuous representation. We are actually thinking about that, but this also kind of imply many problems, because if you use continuous representation, you cannot use the negative log likelihood in the output. You need to use mean-square error, which is a nasty objective. But at the moment, it's not clear to me what is the best way to go. So I probably need, we are working actually with one of my students, Artem. I don't know if Artem is here, but our goal is to assess which kind of path is promising, like staying with audio tokens or go in the continuous world and see what happens, right? And add some kind of tricks to make the continuous world working well. Yeah, I think there is room for two types of research here. Research that improve the current audio tokens and research that instead totally redesign the way we inject audio in multimodal LLMs.
Okay. Thank you. Then there is somebody else who asked, why is SSL, then clustering and discrete tokens called semantic tokens, as the task like emotion recognition requires acoustic information as well?
Yeah, that's actually, as I said, I don't like the term semantic tokens, right? It's commonly used in the literature. That's the only reason why I use it. And I think semantic tokens was like mentioned to highlight that these SSL models tend to extract high-level information rather than low-level information. But the reality is that they can have a mix of them. So I think the term semantic tokens is a little bit misleading, and hopefully it won't be used too much that in the literature. But that's how it's called in the literature. Yeah.
Okay. Another question says on slides 16 and 17, what is SSL continuous baseline?
Okay, so we said 16. Okay, this one, right? Okay.
Yeah.
So here, our goal was to compare the discrete audio tokens with some kind of corresponding continuous baseline. Like as far as I remember here, we trained a model with the wave LM, right? The continuous representation, and we, instead of feeding into the downstream task the discrete representation as we did here, we feed the so instead of feeding the discrete representation, we feed the continuous representation directly without any discretization. This experiment was like designed to assess the performance gap between audio tokens and continuous and standard continuous system, right? And it looks like the gap is evident and still there. And yeah, that was the main reason behind this experiment.
Okay. So Lynn raised her hand. Maybe you can ask her question.
Thanks. Thanks for your talk and nice to see you again, Mirco.
Hi.
May I ask a following question from your discussion with Yiju? I'm new to this topic, so I'm not very sure whether my question is quite simple. So my question is that, as you said, the semantic token and the compression token might have complementary information. And you mentioned the massive multitask would be one way to combine those information together. And another way might be fuse the semantic token and the compression token together.
Yeah.
How do you think about those two?
Yeah, there is a line of research, right, trying to fuse these words. It's called hybrid tokens. But our experience with current hybrid tokens, there are many others now that there are in the literature, so maybe we will assess more of them. So for instance, speech tokenizer is one of these hybrid tokens where you kind of combine semantic tokens and compression tokens. And as you can see, performance is not really good. So maybe at least according to what we see. So maybe this is not the best way to go, or there are better ways to kind of combine the tokens, right? My bet is that we need to focus on compression-based tokens and just train them in a much more powerful way than just like aiming for reconstruction.
I see. Thanks for your sharing.
No problem.
And another question, you already mentioned a little bit about that. You mentioned you have planned to expand your discrete audio and speech benchmark to including more tasks. And I also noticed that the research, you also mentioned that codec Superb and ESP.NET codec. So what's the difference between your benchmark and theirs? And how will you expand your benchmark? Thank you.
So we are expanding it a lot. Pune is here as leading this effort, so she can comment a lot. But we're gonna have like more tokenizers, more tasks, etc. And I think there are differences, right, between what we do in DASM and what is done, for instance, in Codex Superb. Maybe Pune, you can comment a little bit better, but I think the main difference is that we ourselves, we focus heavily on this kind of downstream task, right? And they focus on assessing in a different way the quality of the representation. But the good things is that we are working all together these days. So we have like a big team that we are working with to kind of combine all these benchmarks and figuring out if there is some kind of common trend, common challenge, and yeah. So every benchmark is a little bit different in the way we evaluate the representation, but actually we are combining things and see if there are some at least common trends that emerge from different groups and different benchmarks.
Yeah, maybe I could also add a couple of things. So for the expansion, we are adding much more new tokenizers because at the time that we started the benchmark, like the main category was list semantic, compression, and hybrid. Nowadays, there are lots of more tokenizer, like a single layer tokenizers, a scalar quantization. So we expand on that front. Also, we add much more music and audio tasks. Regarding like a main difference between Codex Superb, ESP.NET Codec. So the main difference is that mostly for many of these benchmarks, they focus on the reconstructed audio. So they so basically they pass the audio, reconstruct it, and then on top of that, for example, they see how the pre-trained ASR model works on the reconstructed audio. What we have done is that we remove the decoder and we try to train a downstream application with a very simple architecture, with a very simple probing head, and see how much information contains inside the tokens. Basically, the main difference is that most of the benchmark focus on the reconstructed audio quality, which might come from the decoder itself, not necessarily the information that the tokens have. And in that, we focus on the diversity of information contains in the tokens, since we train the model directly on top of these tokens. So yeah,
I think that could be more informative, right, for multimodal LLMs, right? Because in multimodal LLMs you feed the internal representation, right? So you're the token, right? You're not feeding, you don't have a decoder, etc., right? So it might be better, right, to assess multimodal LLMs. Yeah.
I got it. Thanks very much for your answering, and thanks for your talk again.
Thank you.
Thank you. Next is Yoshiki.
Can you hear me?
Sure.
Yes, we can.
Great. Thank you so much for your sharing the impressive result, and I'm happy to hear the progress in this field. My question is model size and architecture, because typically the Hubert or WebLM uses the transformer, while the DAC and codec depends on the convolution and sometimes with LSTM. And I guess the model size of Hubert or WebLM is much larger than encodec or DAC. So in that perspective, maybe the general the compression model lags behind due to the modeling capacity. And for example, speech tokenizer uses convolution plus LSM and distills WebLM or Hubert. So in theoretically speaking, I guess if the model capacity is enough, the speech tokenizers model rate should be much more closer to the Hubert or WebLM. So how do you think about the model size or architecture is important in terms of the tokenizer perspective? Because the codec should be smaller in some smaller architecture is better for a codec in some applications, but in the tokenizer perspective, I'd like to hear your opinion.
Yeah, I totally agree with you, right? In part, these compression-based tokens were developed not for multimodal LLMs, but they were developed for compression, right? For transmitting data, storing data, these kind of things. As a result, they had to use architectures which are much smaller than what are used like in the standard SSL models, which instead are designed for other tasks. In that sense, I think I definitely think that scaling up these compression-based tokens with bigger architectures, as I said, multiple tasks is definitely the way to go. So I would say if it is me, right, I will bet that the future will be in the future, this compression-based token will be better than semantic-based tokens just by making them bigger, maybe training with more data, more diversity, and as I said, multiple tasks. So that's what I expect. Yeah.
So that it could be one direction to develop a new tokenizer on top
Yeah.
of the speech plane. I see.
Definitely,
Yeah.
definitely. I definitely think that compression-based token is the way to go in the end. Yeah. Even though at the moment they are not optimal, but it is definitely the way to go.
I see. I see. Thank you so much for sharing your opinion.
No problem. You're welcome.
Thank you. There is someone in the chat who asked on slide 10
Okay.
regarding the model architecture.
Okay, let me go to slide 10. Okay. Yes.
Yeah, so are attention weights being calculated across all layers and again being added with primary embedding?
Yeah, so here you have like for every token, right, you have a corresponding embedding, and you add an attention mechanism, right, to perform a weighted sum of these like the tokens correspond to the different layers with an attention weight that depends on the specific task, right? So this is the attention is learned. So for some tasks you may have like higher attentions. For some other tasks you can have lower attention. So this is actually what we showed here, right? Yeah.
Yeah, and then someone said in the attention plot, we saw that for TTS task, low-level layers perform better.
Yeah.
What does this signify for the low-level layers? Are these more semantic than the high-level layers?
I think here TTS seems to prefer some kind of low-level information, right? On the other hand, people were doing TTS for since like a few 1 year ago or 2 years ago, they were doing TTS like estimating the spectrogram directly, right? So I think here the preference is like for low-level information in general, right? Maybe not as low as a spectrogram, something a little bit higher, but yeah, something like that.
Okay. And then Yadav has a question. He is on mute.
Yeah.
Hello.
Hello.
Hey, hi. So I was wondering, like, why for solving the ASR task, the information is called high-level information, and for solving like speaker verification task, it is called low-level information.
Yeah. So I think the term here, high-level information, refers to when we want to solve like a problem like speech recognition, right? Our output is a text, and the text does not depend on many low-level things like the speaker identities and this kind of thing. But the text really depends on the phoneme content, essentially, right? And this can be considered as a high-level information. Right. Instead, when you do speaker verification, etc., you might benefit from low-level informations, which are in the signal, for instance, the pitch, the format, and this kind of way that are really related to your vocal tract. So, and this is a low-level information that you can find in the early layers of the architecture. Why, when you move on with the SSL architecture, you kind of abstract away this kind of low-level information, and you have something more operating at the level of phonemes, which instead is helpful for speech recognition.
Okay, so like you're saying that what we observe from this heat map, because lower layers are more active for speaker-based tasks such as speaker verification, that's why they are called low-level information.
Yeah.
Am I right?
Yeah, essentially layers in SSL model, layers like the first layers provide low-level information, right? And as long as you move on with the layers tend to provide higher level information, right? So
Okay.
so if this like as a neural network for speech processing, you may expect that these layers contain kind of speaker information, and you move on, and you can until you have like layers having high level information, such as, for instance, phoneme content.
Okay. Okay, so let's say for some reason, like the later layers are active for speaker verification task and earlier layers are active for phoneme. Then will we call phoneme recognition like requiring low-level information?
No, ASR is like enjoys, right? If you see here,
Yeah, so I get it.
I think
I get it. Like
the
for this
more red
case,
is it, the more
yeah,
higher information is. So this is like high level information, not low level information.
yeah. So, but like I was thinking, let's say theoretically, hypothetically, it is like switched. For some reason, there is some encoder which is giving you attention map in a different way. For example, the TTS and SV, the darker reds are on the later layers. Would you still call speaker verification information is low level?
Yeah, exactly. Here there's encoder, still low level information, right? So in this like neural network, you have different types of information from low level to high level, right? And normally if you don't want to call low level or high level, maybe lower level, higher level, but yeah. And normally this is the way a neural network works, right? So you kind of have a different level of abstraction from low layer to high layer, right? And from low level information to high level information.
Okay, thank you.
You're welcome.
Thank you. So there is somebody else who wants to ask a question.
Yeah, I think I do. Can you hear me, Mirco?
Yes.
Sure. Hi, Heitor.
Oh, hello. Thank you so much for the talk. It was amazing. I had a kind of an open-ended question, I think, related to the discrete methods that we are using, like for the semantic tokens. So, for instance, we are using k-means on top of wave2vec or Hilbert or wave-LM. But some of those methods, they already operate on they already have like discrete objectives, right? So Hilbert, for instance, is trying to predict discrete tokens from pre-initialized k-means model. Have you tried to use those directly discrete outputs from Hilbert instead of like doing again another k-means on top of those continuous representations?
I'm not sure. Yeah, that actually could make sense, right? Not sure how much flexibility you have this way to detect the number of clusters you want, etc. But maybe people already have done. I'm wondering, Pune, if you have seen working like that, like exploiting the kind of a discretization which is done during training of Hubert and also WaveLM, right?
Yeah, like the main works in the semantic tokens, mostly people use training a new k-means for multiple reasons. The first one is like the flexibility. So you could come up with different number of clusters. You could use the data set that you want. And also most of the time, like these discrete tokens, original discrete tokens from Hubert, for example, only is on the last layer, if I'm not wrong. But most of the time here, people think about what would be the best layer to use for quantization. I have seen maybe one or two works that use these discrete tokens, but for sure the main literature here use the train a new k-means, just because of all of this flexibility that it has.
I see. I have a follow-up question. I'm totally new to the topic. Sorry, so if it's a little bit simple question, but also I was curious to see if you guys have noticed any works trying to use, instead of like large speech encoders, but try to leverage compressed speech encoders, because usually those models, they are trained to try to maximize the mutual information between like the representations for a large model to a smaller one. I was just curious to see if maybe in the new version of the benchmark, you guys are looking to try different encoders, like smaller encoders, like GCU Hilbert or others.
Compression-based tokens are normally very small, right? So, but for semantic tokens, yeah, I think we can try. Normally, what we would like to do here is to just like stay as aligned as possible with the literature. So if something come out there, we can keep track and inject in our benchmark. But generally speaking, I'm not a super big fan of the semantic tokens. As I said, I think compression-based tokens will be the best way to go. And the reason is that in in compression-based tokens, you learn everything, right? So you learn a discrete representation from scratch, essentially, right? With the
Yes.
here, like the semantic tokens, they are not differentiable because you have to pass through the k-means, and it's not obvious how to make an entire pipeline differentiable. Even though there's like semantic tokens, they work well these days, I don't think is the best way to go in the future. So yeah.
All right. Thank you so much.
You're welcome.
Thank
Hi,
you.
Mirco, can I ask a follow-up question on that?
Sure.
It's because you mentioned like that the compression way is the way to go, and I wonder if that's because of the training efficiency, or is it because of like just in general how their training like objective is?
I think in the compression-based tokens, like you really learn the discrete tokens, right? End to end, right? So with semantic-based tokens, you need to first train continuous representation, and then discretize them with k-means, right? And this process of this discrete is there's like clustering thing. Is not that you can like embed in a neural network and things like that. So this has like is very limited in my opinion, and there are a lot of heuristics that are needed here to make this work. And we did a paper on that, so I think we are able to make that working very well. But the reality is that there are so many heuristics to set, number of cluster, number of everything, which in the end, it is better to train everything end to end, right? With more data, bigger models, and things like that. Yeah.
Thank you.
You're welcome.
Okay, I think there are no more questions.
Okay.
Thank you. Yeah, thank you, Professor, for the talk. Thank you for the questions.
No problem. Let me thank everybody for attending and for asking many questions, and you, Hiba, and Pune for for like organizing that.
Thank you. So we will resume after the break, after the holidays. And yeah, happy holidays for everyone.
Yeah, so
Yeah.
basically we don't have meeting for 2 weeks, but then we will return back on January 9th. We have Haibin Wu from Microsoft, who is also talking about the neural audio codecs in the era of a speech language model. So he is the first author of Codex Superb. So yeah, stay tuned. We have lots of great speakers in the 2025.